January the 2nd, 2016. This is an updated version of one of the ones that got took down, guys. It's about Asteroid 2013 TX68. Let me pull this up. Notice yesterday's date is when I started the model, January the 1st, when I actually began the video. This thing is behind Earth and slightly below us. It's going to come very close, one of the closest that we've ever seen that we knew about that was coming. Now, as I advance this up into March 5th, what you're seeing is two colored blue lines. Watch this in 720 HD if you can't see them, because that's what it's recording in. The dark blue line means that this asteroid is below the ecliptic of our inner solar system planets. The light blue line is when it rises. On the back side, it was diving in, going around behind the sun. And as it comes around exactly on March 5th, it rises from below us, the southern ecliptic, into the northern ecliptic. And that's where it goes back to the light blue line. So it will be coming below us and from the sun side. According to their models, and we'll go through that data, which is a lot of information in there that's very different from other asteroids. It's showing about 1:15 p.m. on the east coast on March 15th. That afternoon would be the close approach data. But this one has some unusual distinctions as far as time of uncertainty and exact moment. Some of these asteroids, they've got down to 0.01 second. Very rarely will you see one go into an hour. Some will be 2 or 3 hours of uncertainty. But this particular object has a 2-day plus uncertainty. They haven't seen it since 2013. It was not this close on the last pass. But they knew up to 0.01 second of the time that it would come to the close approach. Now, they only saw it in 2013 for 3 days. This is important. From October 6th through October 9th, observations used totaled 32. That means that's how many they put into the model. The condition code is also important. The solution date was June 13th, 2014. Now, looking at the condition code 7, and many of you have seen this before, but I get so many questions, I try to go over it. 0 to 9 is how it's listed. 0 is good, they know where it's going. 9 is highly uncertain. We're at 7, we're on the high end of uncertainty. Now, if you put in the data, and this is what this is at the bottom chart, you'll have to pause this and study it. I did. It took a long time. It's going to pass by the moon about 3.5 hours before it passes by the Earth. The moon, it will pass by, according to this, at 7,593 miles, 14,000 miles from the Earth, 14,673. But we got to look at these numbers even closer. Now, when you're talking about 14,000 miles, our geostationary satellites, DirecTV, many other ones, are at 24,000 miles, 22,400, excuse me. So we're diving well below our communication satellites, many others. That's called the geostationary band. But this is, if you pay attention to the way they do this, they measure from the center of the planet. Look at the top. Distance from the center of the Earth to the center of the object. See the NASA JPL Solar Systems Dynamic Glossary, and it will tell you this. So you've got to take 3,976 more miles. That's what 6,400 kilometers breaks down to. So we're dealing with the real distance in the model of 10,696 miles from the outer edge of the planet. Remember, they go what's called geocentric, from the center of the object. So we're dealing with center of asteroid, center of the planet. So you've got to deduct for that. But the level of uncertainty is not just in the numbers. It goes into the details of the data. Notice this. I could stay on this chart for a day. March 5th at 18:15 UTC time. That's 1:15. That's in the bottom left, guys, with the arrow. But look at the time of uncertainty. 2 hours, 13 minutes, and 39 seconds. Back in October, when they saw it, they had an uncertainty of 3 lines up from there of 0.01 second. Now, this is just a chart of close approaches back. And if you read the whole chart, and you can go to JPL, I'll put a link there, and go through every one up into the modern times, you will see that the time is always in seconds. There's a couple of instances where you go to 3 hours, 2 hours. That's the max. Never do you see time of uncertainty at 2 days, 13 minutes, and 39 seconds. Right above that, you're at 2 days, 14 minutes, and 4 seconds as far as the time that it passes the moon. Look at between 1449, 1815, roughly 3.5 hours. Now, something else interesting, good for math. It passes the moon, and at that point, it's about 2,000 miles per hour faster than when it goes by the Earth. Something else important to remember here, and again, this is the type video you got to pause. The Earth is moving at 67,000 miles per hour forward in rotation. That's fast enough to cover the planet's diameter in 7 minutes and the distance to the moon in just 4 hours. So if we have an uncertainty of 2 days, and we're only dealing with 14,000 miles minus that 4,000 because they went from the center of the planet. Another key thing is not only the close approach is very, very close, but the size. At the magnitude, the chart, it's listed at 25.3 on the far right. That's going to be about 55 meters or 180 feet wide. Asteroid coming in. Now, quick on this chart, here's the two objects, the Earth and the asteroid moving to a crossing point. Asteroid's moving now because it's not at the Earth at 34,000 miles an hour, about half the speed of the Earth, but it has an inside angle on a much tighter circle. That's why the model has that rendezvous point. You also have to figure in that it's going to be slower down to 32,308 miles as it gets close to the Earth. Now, that's unique in that, and I'm going to show you the record of close approaches, but the size is key. You don't think 180 feet is that powerful. We're going to look at an example of a couple of asteroids. Listen, and remember, this one is 55 meters, 180 feet. We got that from the magnitude. Now, this is a timeline of close approaches. You can pause this and look at it. Third column over, it gives you the kilometers in the nominal distance. You see that? That's the close approach. The two on the bottom are the only ones that's even close. Look at the size, 1 meter, not 55 meters. Now, one of them that struck was this one in Russia. Remember that in 2013? It was estimated to have the mass of 12 to 13,000 metric tons, heavier than the Eiffel Tower. And you can pause it again, 20 meters in diameter. Many of you saw the videos. I did a couple about it. This one's 55 meters. Now, if you remember this Russian meteor that we covered, we were watching 2012 DA14 on the other side of the Earth. They didn't know this one was coming. But again, it was the first one that resulted in a large number of injuries. When the shock wave arrived, minutes after the Super Bowl lights flashed, 7,200 buildings in 6 cities were damaged by the explosion. Authorities were scrambling. You saw the videos to repair the structures in sub-zero. It looked like a nuclear shock wave. It was blowing large doors in on buildings, and people were inside. It was very fast impact. The shock wave after it exploded, you saw in the videos. This is in Arizona, Behringer Crater. You're looking at an example of the 3 pyramids in Egypt sitting inside the crater. This rock was smaller than the one we're looking at. If you read this, 40 meters. We're dealing with 55 meters. Again, the crater is 1,200 meters in diameter, 170 meters deep. The interior of the crater contains about 220 meters of rubble overlying bedrock. Crater was formed 50,000 years ago. We're dealing with unusual events and the uncertainty. I'm not saying this thing will hit the Earth. When it's this much uncertainty on the time, and it's this large coming this close anyway, we see a slowdown in the data of 2,000 miles from the time it comes by the moon to the time it gets to the Earth, 3.5 hours later at that speed. There's a lot of math involved in doing the calculations. Again, if the model was correct with a 0 degree of uncertainty, it would be at 1:15 p.m. East Coast time, U.S. on March 5th. There's a lot of information here. We're going to update it once they spot it, or what they call recover this object. I'm sure they will update the model. But the last pass in 2013, guys, was not nearly this close. So it's got what would be called at this point a declining radii. And that has to do with where the Earth is at as it comes through the solar system. But I promise this, and I've been busy. It's a heads up. Be safe.